Okay. In this section, what we are going to do is look at the conservation laws as the conservation laws which we obtain from Newtonian mechanics, but of course, in case of Lagrangian mechanics you can do little more. Now, what we have here in Lagrange's equations are 2n differential second ordered differential equations, and they are given by del L by del q I minus d by dt is equal to 0. So, these are the 2n differential equations. Now, when you find the complete solution to this system of differential equations, you actually find each of these coordinate functions or coordinates as a function of time t given some initial conditions, and it is in terms of t and 2n arbitrary constants or constants which are given in terms of either initial conditions or the boundary conditions. Now, what will happen is this: most of the time we will not be able to find the complete solution, but even if we do not find the complete solution, it is still all right, because if we can do at least one integral, that helps us a lot. And in fact, in the number of cases what we find is that we can actually do one integral which is called as first integrals, and these first integrals typically can be put in a neat functional form like this. So, some function of q dot and t is equal to constant. So, what will happen is, in this equation there is only q dot. So, you have first order differential equation in t. So, once we get this is also important, because this does give us the information about the nature of the actual system. Now, the conservation laws actually are built at this level itself. So, to take an example, consider the case of cyclic coordinates. Now, in cyclic coordinates, if Lagrangian is independent of one of the q variables, say independent of q j for some j, okay, for some specific j. If it is independent of q j, then del L by del q j becomes 0, and you immediately get a rule. So, d by dt of del L by del q j dot is equal to 0, and which means del L by del q j dot actually is conserved quantity. It remains constant throughout the motion of. And if you look at this quantity here, if q's were Cartesian coordinates, then you immediately identify this quantity to be the linear momentum. So, for example, for case of a free particle in 2 dimensions, so your Lagrangian is half m x dot square plus y dot square, and this Lagrangian is independent of both x and y. If I just look at x, then this immediately tells us, because Lagrangian is independent of x, that del L by del x dot must be constant, and that in fact is nothing but m x dot is equal to constant, and m x dot, remember, is nothing but the x component of the linear momentum. So, in this problem, of course, also y is absent from Lagrangian, my dot, that is linear momentum in y direction, also will be conserved. In fact, the net linear momentum gets conserved. Another example would be if I take the same situation, but write the Lagrangian in terms of polar coordinates, then now you see this particular Lagrangian is independent of theta, but it is not independent of r. Okay. So, what gets conserved here? Because theta is absent, theta is not present, this immediately tells us that del L over del theta dot, and this in this case will turn out to be m r square theta dot must be constant, and this we immediately recognize as angular momentum. So, in both these cases, if a particular coordinate is missing from the Lagrangian or Lagrangian is independent of that coordinate, the corresponding quantity del L by del qj dot remains constant. And by analogy with these two examples, if I am talking about a Cartesian coordinate, then the corresponding quantity del L by del x dot is a component of a linear momentum. If it was theta, then it is an angular momentum. So, by analogy with this, the quantity del L by del q dot is in fact named as conjugate momentum or generalized momentum. And remember, this is always conjugate to a given coordinate. So, I will write it as P j defined as del L over del q j dot, and the conservation theorem now says that if L is independent of q j, then the corresponding conjugate momentum P j is conserved. And also we have to remember that P j is not necessarily a momentum, it does not have necessarily dimensions of linear momentum. What we have shown here is that in one case it turns out to be linear momentum, in another case it turns out to be angular momentum. In more complicated cases, which I will do in the next week, for example, if you have charged particles in electromagnetic field, even then we can write down the Lagrangian for this system, and in that case the conserved quantity for a particular coordinate is in fact not just the mechanical moment of the massed or massive charges, but it actually is a combination of the mechanical momentum plus the momentum carried by the electromagnetic fields themselves. See, the total of these two is actually conserved. So, what we are talking about here is not necessarily the momentum of the system or even the momentum itself, but some quantity which we call as conjugate momentum or generalized momentum, that is the quantity that is conserved in this case. Okay. Now, in the same way, I can also derive from this point on, I can also actually derive the normal momentum conservation law which we get from the Newtonian mechanics. Say, take for example, we have a mechanical system. So, there are n particles and the coordinate or position vectors of these n are given by n, okay. And we are using generalized coordinates. In this case, I will for simplicity use only unconstrained system. So, I have generalized coordinates which we denote by q, but includes q small n, these many coordinates. Okay. And now, what I will do is this. See, it is very common for example, one of the examples when we were discussing the generalized coordinates is it is very common to choose one of the coordinates to be center of mass coordinates. So, let me assume that in this there is one variable q j, okay, for some specific j, and the role of this q j is thus. When you take the system, and if I keep all the q's fixed and only change q j, then the entire system is translated by exactly the same amount. Okay. So, each one of these Ri's will translate by exactly the same amount. So, what I mean is this. So, Ri at, so for each I, Ri of q1 qj plus some small epsilon and qn t, this is equal to Ri at q1 to qn including qj t plus some n vector times epsilon. Okay. So, all position vectors shift in the direction of n and by the same amount, which is magnitude of n vector into that small constant epsilon. Okay. So, this is of course for small epsilon. Okay. What happens to the velocities? Velocities of course will remain constant, because if I take Ri dot here at qj plus epsilon and all the way up to t, this also will be equal to Ri dot at q1, q2, qj and all the way up to t. And because n times epsilon is constant for all of the position vectors, its derivative would be 0. So, all the velocities are unaffected by this translation of the entire system. So, what must happen is this: if the velocities are unaffected, what happens to t? T, which is kinetic energy, which is sum over half mi Ri square, this is independent of qj. Okay. Or in other words, I will write this as del t by del qj is 0. And look at what happens to del t by del qj dot. So, del t by del qj dot, this is nothing but sum over I mi Ri vector dotted with del Ri vector by dot del qj dot, and this we remember is in fact equal to half mi Ri dot into del Ri by del qj. Remember, while we derived the Lagrangian equations, we had this identity proven, and this of course is equal to half sum over mi Ri dot, but what is del Ri by del qj? Oh, look at this one here, that is nothing but dotted with the factor half of course will not be there. So, delete the factor of half. Okay. This is nothing but n vector times epsilon. And what is this? This is nothing but total momentum, which is sum over mi Ri dot vector into epsilon. That is it. Okay. And what happens to the potential term? We have already seen that the kinetic energy term will be independent of qj. the potential energy term. So, del V by del Qj, we will of course at least for this case assume that the potentials are independent of velocities, okay. In which case this is in fact nothing but sum over I, and you have gradient of I with respect to V into del R I by del Qj, and this is nothing but sum over I, this is minus F I into, and again this is nothing but n vector times epsilon. So, the Lagrange's equations are actually in this case for Qj will be nothing but d by dt of total momentum dotted with n is equal to summation over F I will write this as minus F total dotted with n times epsilon. Of course, I can immediately remove the, and what happens when you have del V by del Qj. So, if the Lagrangian is independent of Qj, then we automatically know that this would be equal to 0 and total momentum is a conserved quantity. Okay. So, if Lagrangian is independent of Qj, corresponding generalized momentum Qj dot del L over del Qj dot will be conserved quantity, and in this case it just turns out that that quantity is a component of the total momentum along n cap vector, and that is the quantity that would be conserved in this case. So, this is the general conservation law for linear momentum of the entire system. We can do exactly the same thing for the angular momentum of the entire system. So, think in terms of, there is a particular coordinate which causes the entire system to turn, okay. Then we will be able to derive a similar law for the angular momentum. Now, I will not do that here, but I will ask you people to try that at home and see for yourself that you can actually derive the same similar condition for the angular momentum case. Okay. Now, I will do one more conservation theorem which we get from the Newton's equations, and that is energy conservation. Okay. Remember, you have a system whose Lagrangian is given by Q, and Lagrangian, of course, whenever you have a path Q of t, Lagrangian is of course a function of time t, and it is a implicit function of time t through variables q and q dot, and it also may be explicit function of time t. Okay. Let me assume that given Lagrangian is independent of t. You see, we will have a identity which is similar to Beltrami identity. So, let me write that here. If I calculate dl by dt, this is nothing but, because there is an implicit dependence, del L over del q dot, del q into q dot plus del L over del q dot d by dt, so of q I dot, okay, and plus there will be a partial derivative with respect to time t. Okay. Now, this we know how to, this can be rewritten as, so d by dt, remember this is similar to what we did in case of Beltrami identity. So, the first factor here del L over del q dot can be replaced by d by dt of del L over del q dot from the Lagrange's equation, and this of course can be written as q dot into del L over del q dot, okay, and then summed over I plus del t, and put it together, this will become d by dt of q dot del q dot minus L t is equal to 0, and the quantity which goes here in the bracket, this is usually denoted by H and is called energy function. Function of the system. And remember, if L is independent of time t, that means there is no explicit dependence on time t, that means partial derivative is 0, this immediately gives us that H is a constant or is a conserved quantity. Okay. Now, how does this turn out to be an energy conservation? That is not immediately clear here, but if I look at one example, it probably will immediately become clear. Again, take one example. Suppose the Lagrangian of the system is of a single particle which is travelling in 2 dimensions under the influence of some potential field. Okay. And the potential field here depends only on the coordinates and not on the velocities. Okay. In this case, I can now calculate the H function, and H function here would become, so this would be x dot, I will first write this explicitly, plus y dot del L over del y dot. Remember, there is a summation over q I. So, here it would be x dot del L over del x dot plus y dot into del L over del y dot and minus the Lagrangian. And can you immediately see that this simplifies to half m x dot square plus y dot square and plus v of x y. There you go. This is nothing but the total energy. This is the total energy of the system. So, at least in Cartesian coordinates, if v is only function of coordinates and not of velocities and time, then you have a conservative system, the total energy is conserved. So, this is the conservation theorem for total energy. But remember, normally H will not be same as the total energy of the system, that can be different. Now, if your Lagrangian has a form like this, I will write this as L0 plus L1 plus L2. Okay. Now, the piece L2 is, say, only quadratic in velocities. So, I will write this as sum over some C I j q I dot q j dot. Okay. Summation is over I and j, and there will be double counting which we will take care of when we write the C I j. Remember, C I j themselves will be function of q1 to qn and probably also time t. And similarly, L1 is a linear term. So, I will write this as B I qi dot. Okay. It is only a linear term in qi dot, and L0, this is a term which does not depend on the generalized velocities. Okay. It is just a function of q and t. In this case, if I calculate h, this is a exercise for you people from the assignment. Show that this will be equal to L2 minus L0. Okay. So, h function just turns out to be this much. In this special case, what happens is this: if I have, suppose you have the position vectors r I and you make a transition to generalized coordinates q. So, when I write this transformation equations r I as r I function of q1 to qn, and if these transformations are independent of time t, then what you get is a homogeneous. So, when you take r I dot, you get a homogeneous function of the generalized velocities, and it is linear in generalized velocities. So, when you take squares, you only get L2 term. So, this, remember, if the transformations are independent of t, then you get L2 term in Lagrangian and you will get L0 term. Okay. The first linear terms in generalized velocities will be absent. Now, what would be L0 term? L0 term is your potential term. In the potential term, if we assume that the potential depends only on coordinates and not on generalized velocities or on time, then your h function in fact will simply become L2 minus L0, and this would be same as kinetic energy plus potential energy. So, in this special case, the h function looks like the total energy or is equal to total energy, and in this case, if your Lagrangian is not explicitly dependent on time, the total energy is conserved. So, that is how we get the energy conservation rule. Remember, h energy function, even though it is called as energy function, it is not equal to total energy, and it may happen that h is a conserved quantity, but your total energy may not be conserved quantity. I will give you one example of this, or even it may happen that h is actually equal to total energy, but the total energy is not conserved. Remember this h function. So, Lagrangian, even though there is a unique Lagrangian, the h function actually depends on the coordinates. So, which coordinates you choose will keep on changing your h function. Now, also the total energy function. So, here is an example which illustrates this. This is a bead on a rotating wire. Okay. So, you have a wire and there is a bead on the wire, okay. And this wire is in fact rotating about origin with a constant angular speed omega. Okay. So, here because there are two coordinates to begin with, but there is one constraint, and because of this constraint all I really need is one generalized coordinate which is r. The other coordinate theta is in fact just equal to omega times t. Okay. Now, let us write down the Lagrangian for this. Lagrangian for this will be half m r dot square plus r square theta dot square, but that we already know is just omega square. Okay. This is the Lagrangian for the system. And what is the total energy of the particle? So, total energy of the particle here, because there are other than constraint forces, there are no other forces acting on the particle. So, total energy is simply half m r dot square plus r square omega square. Okay. And what is the h function? Let us calculate h function. So, h function will be, energy function will be equal to r dot del L over del r dot minus L, and this is half m r dot square minus r square omega square, minus r square omega square. See here the h function is not same as energy function. Now, let me ask you a question. Is this a conservative system? That means, is the energy conserved quantity here? Surely not. See, if I had a free rotating rod like a merry-go-round which is not driven, and if you sit on it and if you move outwards, what would normally happen is the angular speed decreases, but in this case, even if the particle moves away from the origin, the external system, the constraint system, is actually driving the rod or the wire with the same constant angular speed, which means the external forces or the normal reaction here is doing work, and that work is actually reflected in the energy E. So, what remains conserved here? Remember, Lagrangian again is independent of T. That means, this is conserved quantity. This is conserved quantity. What does this mean? How do I interpret this? In fact, we can immediately see that if I hold the particle at t is equal to 0 or at some initial instant and let go, that means at the initial instant r dot is 0 and your h function is in fact nothing but, so at t is equal to 0, r is equal to r naught and the speed, the radial speed of the particle is 0. So, we are letting go at one instant. So, this is in fact minus half m r naught square omega square. And what it says is this: if the particle moves out to some other location, then its new energy will be same as this quantity plus the amount of work done by the constraint forces. Okay. That is why the difference between h and E is exactly equal to m r square omega square. Okay. So, the difference, the gain in the energy would be m r naught square omega square. This would be total amount of work done by the constraint forces. So, in this example what we see is that the total energy is not conserved, but as long as the Lagrangian is independent of time t, there is some conserved quantity which is called as energy function, and that energy function is given by this in this case. Okay. Now, these ideas in fact are also related to, each one of this conservation principle is related to the symmetries of the Lagrangian, and this is going to be focus of my next section. So, the conservation laws are intimately connected to the symmetries of the Lagrangian, and this is going to be focus of this small section today. If you see that if you make a coordinate transformation, this is a great facility given by the Lagrange's equation, for a very simple reason that the general form of the Lagrange's equations remains same. What that means is this: when I make a transformation, the Lagrange's equations as we write them. So, if we start from the coordinates q, which are given by q1 to q1, and make a transformation to s, which is s1 to sn. So, the transformation here would be qi is written in terms of s1 to sn for each qi. Okay. Under this transformation, the form of the Lagrange's equation remains same. That means d by dt of del L by del qi minus del L by del qi, this is equal to 0. This is if it is Lagrange's equations for q coordinates. Then for s coordinates, it is the same equation, except that si dot minus del Ls by del Si is equal to 0. The only thing is the Lagrangian of course changes. The Lagrangian will be given by the new Lagrangian, which is function of s, s dot and t. This must be obtained from the previous Lagrangian, which was written in terms of q, but remember q is a function of s and possibly also t. Then q dot will be function of s, s dot and t, and the explicit dependence on t. So, this is how the new Lagrangian is calculated, but the general form remains same. This is not true for the coordinates though. Even though the general form is same, the individual equation when you substitute coordinates will be different. I mean, you cannot simply take this equation for qj and substitute sj in that equation to get a new equation here. What I mean by this is that if you start with Cartesian coordinates, let me take simple example where you go from xy coordinates to r theta coordinates, and the Lagrangian is that of a free particle. So, you have half mx dot square and plus y dot square. So, when you make a transformation to the new Hamiltonian, new Lagrangian, Ls, which is function of r theta, r dot theta dot and so on, this would come to half I dot square plus r square theta dot square. So, the Lagrangian looks different. What about equations of motion? Oh, they also looked very different, because in first case the equation simply turns out to be mx double dot is equal to 0 and my double dot equal to 0. But so these are the equations in x and y, but in r and theta we already know that mr double dot minus r theta dot square must be equal to 0, and the second equation for theta becomes m r theta double dot plus twice r dot theta dot must be equal to 0. You see, I cannot simply take the x equation mx double dot, substitute r in it and write down the equation for r. That is not true. So, even though the Lagrange's equation in the form are same, the actual equation in terms of coordinates, they will be of course different. Now, when will they be same? They will be same if the Lagrangian has the same form. Now, that also I will explain using an example. So, you start with xy coordinates and go to new coordinates which are x prime and y prime, and these x prime and y prime are basically obtained by rotating xy frame by an angle alpha. So, the connection would be x prime will be equal to cos alpha times x plus minus sin alpha times y, and y prime will be equal to sin alpha times x plus cos alpha times y. And the original Lagrangian here, which is function of x y x dot y dot and t, this is half m x dot square plus y dot square. And what is the new Lagrangian? Great. Now, the new Lagrangian also has exactly the same form, which is equal to half m x prime dot square plus y prime dot square. And you see, this is what is called as the invariance of the Lagrangian under coordinate transformation. Even if you go from here to here, the Lagrangian form of the Lagrangian is same. And in that case, of course, because the general form of the Lagrange's equations is same, here I can find out the equation for x prime simply by taking equation for x and substitute by x prime, and that immediately gives you this equation. And similarly, m y prime double dot will be equal to 0. So, these are the new equations obtained from the new Lagrangian. So, I will call this as LS. This was a new Lagrangian. So, this is the idea that we want to follow. Under which transformations the Lagrangian remains invariant. Okay. So, make a general case. We have a system with n degrees of freedom with one set of variables which are q1 to qn, and we are making transformation to another system, another set of coordinates which is s1 to Sn, and the transformations here is Si are given in terms of q1 to qn and possibly t. Now, of course, when you make this coordinate transformation, all the other conditions of differentiability and the invertibility must hold here, and we will assume that these transformations are called as point transformations. Okay. And then we get new Lagrangian Ls, which is function of s, s dot and t. So, remember, this is in some sense definition, which must be equal to L at q, but now written as function of s and t, q dot, which is written as function of s, s dot and t. So, you have to basically take this transformation, find the inverse transformations, and in the Lagrangian, wherever there is a q, you substitute the form in terms of s. So, this is what you get a new Lagrangian, and then we will say a Lagrangian is invariant under a point transformation if the new Lagrangian has exactly same form as old Lagrangian. Remember, This means you take the form of old Lagrangian, wherever there is a q, you substitute by s, where there is q dot, you substitute by s dot. Okay. This is called as, and then the point transformation is called as invariance transformation. So, when you have invariance transformation, the Lagrangian remains form invariant. Where is the example? So, there it is. In the previous two examples, this one here, this transformation is not an invariance transformation, because if you take a new Lagrangian function of r and theta, wherever there is a r, substituted by x, wherever there is a theta, substituted by y, will not work. Okay. So, this one is not an invariance transformation. But this one is here. This one is an invariance transformation. For this particular system. Okay. Now, what is the connection with the conservation laws? So, there it is. So, you get conservation laws. I will first consider the simplest possible case of cyclic coordinates. Remember, a coordinate qj is cyclic if L is independent of qj, and we already know that if this happens, then quite obviously the corresponding generalized momentum or conjugate momentum is conserved. Now, we will see what is the connection of this statement with the symmetry of the Lagrangian. Think of this, a transformation where S I is equal to Q I if I is not equal to j, and S j is Q j plus some alpha. Okay. And you can immediately see that the new Lagrangian here, which is S1 to Sn, S1 dot to Sn dot t, this is in fact exactly equal to Lagrangian, the old Lagrangian at S1 to Sn, S1 dot to Sn dot and t. That is because each Si is in fact same as Qi. So, that is what goes into the Lagrangian, and Sj is different from Qj, but wait, your Lagrangian does not even have the term Qj. So, it will not have Sj. So, this in that case holds. That means, if Qj is cyclic, then L is invariant under translation along Qj. See, what we have done here is in fact keeping all other coordinates same, we have just translated the system along the coordinate Qj. Okay. So, under the translation transformation or the system here, the Lagrangian here is invariant under the translation transformations for or along the direction of Qj or along the coordinate Qj, and this results in the conservation law that Pj is conserved. We will see exactly which quantity is conserved in this case. Okay. The connection right now we have this statement, Qj is cyclic Pj is conserved, Qj is cyclic, Lagrangian is invariant. Now, we want to put these two together and say that if the Lagrangian is invariant under a particular transformation, there is a conservation law. Okay. All right. So, let me do that here. So, let me start by taking a Lagrangian of q dot and t. Okay. And we will say that we have this infinitesimal transformation which takes each qi to qi plus some delta qi. Okay. With this transformation, what would happen to the Lagrangian? If qi is changed like this, then qi dot are also qi dot plus delta qi dot. Okay. And let us put this together. So, if under this transformation Lagrangian is invariant, implies that the Lagrangian as a function of coordinates q dot and t also must be equal to Lagrangian, substituting the new coordinates now, qi plus delta qi dot plus delta qi dot and t. And you can of course expand this. So, this would become Lagrangian at qi dot and t plus sum over I, and then you have del L over del qi into delta qi plus partial of L with respect to qi dot into delta qi dot. Okay. And then of course, we can immediately say that you remember the trick that we did in case of Beltrami identity. This is nothing but replace del L by del qi dot here by d by dt of del L by del qi dot. And then this just looks like a product rule for differentiation, and I will put this. So, the Lagrangian of course will cancel on both sides, and what you get is d by dt of sum over qi dot into delta qi, and this is a conserved quantity. So, there you go. For every infinitesimal transformation, which more accurately are called as continuous transformations, for an infinitesimal transformation, there is a conserved quantity. We will immediately look at the examples of this. So, let me take an example of a 2D harmonic oscillator. Here the Lagrangian is y dot square plus half m omega square x square plus y square. Okay. And now I am going to do a transformation to new coordinates. So, if I take x prime, which is, remember, this is same as the rotation of the system by an angle alpha, but now I am going to assume that the angle alpha is infinitesimal. So, if angle alpha is infinitesimal, then I can write x prime as x minus alpha times y, and y prime will be equal to alpha x plus y. Okay. This immediately gives us delta x to be equal to minus alpha y, and this gives us delta y is equal to alpha x. And if is this particular Lagrangian invariant under such a transformation? Yes. If you substitute all this there, then the new Lagrangian will be equal to half m x prime or x dot square plus y dot square plus half m omega square x square plus y square, and plus the term which are quadratic in alpha square. So, all the linear terms in alpha actually have vanished, leaving the Lagrangian invariant, at least in infinitesimals, invariant under this transformation. And what is the conserved quantity then? So, conserved quantity will be del L by del x dot into delta x plus del L by del y dot into delta y, and this is a conserved quantity, and we can immediately identify this. What is del L over del x dot? That is nothing but m x dot. And what is delta x? Delta x is nothing but minus alpha times y. And for the second term, this is my dot into alpha times x, and this must be constant, and this immediately gives you alpha times m times. So, this will be x y dot minus y x dot is constant. And what does this immediately tell you? That this quantity also must be constant of motion, and this is in fact nothing but z component of the angular momentum. So, in this case it is very obvious that there is a symmetry, circular symmetry or cylindrical symmetry in xy plane, in which case the z component of the angular momentum is conserved. So, this is how the conservation principles emerge from the invariance of Lagrangian under point transformations. And another example, in this example I will take a simpler case, or here the Lagrangian is half m r dot square plus r square theta dot square, and let me assume that the potential only depends on r. This situation is similar to the previous one. Okay. Situation is exactly same, because in the previous case the potential I had explicitly given it as a potential of the harmonic oscillator, which was proportional to x square plus y square, and that means it is proportional to r square. Here what we are saying is that the potential here does not depend on the angle theta, which also makes theta a cyclic coordinate here, remember. And the transformation that we are going to do is theta prime is theta plus small alpha. Okay. Small alpha. This is like a translation along the theta direction, which eventually means a rotation, which is exactly same as the previous example, but here the transformation looks like, when you look at it from the coordinate theta point of view, it's like a translation by small amount alpha. And in this case, again the conserved quantity will be, so here delta theta is alpha. What is delta r? We are not changing r. Okay, so the new coordinate r prime is exactly equal to r, which gives us delta r to be 0. So this is a translation where all the coordinates are fixed except one, which is being translated. The conserved quantity then would be equal to delta r into del L over del r dot plus delta theta into theta dot, and in this case this will be equal to constant. But this of course is 0 plus delta theta is nothing but alpha, and del L by del theta dot is nothing but m r square theta dot is equal to constant. This is again the z component of the angular momentum. So there is a intimate connection between the invariance of Lagrangian or symmetries of Lagrangian to the conservation principles. So for every continuous invariance transformation, there is a conservation law, and the conserved quantity is also given by, so for every infinitesimal transformation, given by delta q, okay, there is the conservation law which states that sum over I delta q I into del L over del q I dot is a conserved quantity. This theorem is called as Noether's theorem. This is by a mathematician, Emma Noether. So it's in the honor of her work. This is called as Noether's theorem. Right. Now, only one last point before I stop here. Remember, the invariance of Lagrangian, the way we posed it here, in fact it is little bit restrictive. If you notice, and this is also a problem in assignment, is that if you take a Lagrangian, you get equations of motion. Now, if I have set of equations of motion, do I have a unique Lagrangian for it? It may be possible that different Lagrangians may give you the same set of equations, and that actually happens. We can immediately or easily prove that if you have a Lagrangian L, you construct new Lagrangian L prime by taking L, which is function of q, q dot and t, and add to it t of q and t, both L and L prime, they in fact will give you exactly same set of equations in coordinates 2. What that means is, when I was defining my invariance earlier, when I make a point transformation, I get a new Lagrangian, and as long as new Lagrangian is equal to old Lagrangian plus a total derivative of some function of q and t, I still get an invariance. Okay. So, the new definition of invariance should also include this. So, L prime at q, q dot and t, if it is equal to old L, old Lagrangian at q dot and t plus another total different derivative of some function, then also your Lagrangian is considered as invariant.